While we are all joining this event from our own location, we would like to acknowledge that we are meeting on the lands of the Wurundjeri people and the Boon Wurrung people of the Southeast Kulin Nation. We would like to pay our respects to their elders, past, present and emerging, and to all First Nations communities joining us today. Hello and welcome everyone to a night at Mount Burnett Observatory. Tonight we are thrilled to take you on a journey through the fascinating world of space exploration and astronomy. We will be talking about the James Webb Space Telescope, or JWST for short, which is set to revolutionize our understanding of the universe. With its advanced technology and impressive capabilities, JWST will give us unprecedented views of the cosmos and help us answer some of the biggest questions about our universe. Whether you're tuning in from around the corner or around the world, I want to extend a warm welcome to all of you who have taken the time to join us here tonight. It is great to have such a diverse and engaged audience. I must remind everybody that any of MBO's live streams will never ask anyone to register and give credit card details. We bring these live streams to the public for free. So please, if you come across an MBO live stream that asks you to pay for it, it is a fake stream and we ask you to report it. Tonight, we'll take a closer look at the technology behind the JWST and learn more about its unique features and capabilities. This will be presented by some of the MBO panelists who will share their knowledge and insights about JWST and its exciting mission. I'd now like to introduce you to our panelists who will be presenting tonight. Could you please join me, Jackie? Merv? Neil? Steve? Andrew?
Good evening, all.
Come on in, Andrew. There you are. Hello. And Ella will be joining us a bit later. Oh, and Stuart, of course. We can't forget our Stuart. Hello. Come on in, Stuart. Okay, all of us here would like to give a shout out, as always, to our fabulous crew who are working hard behind the scenes on Facebook and YouTube. They too play a big part in bringing this production to you. We also have Jet and Neil, who are our producers for this evening. But this event is not just about learning about JWST, it's also about sharing our passion for science and exploration with each other. It's about the connections we make and the discussions we have as we explore the wonders of the universe together. Throughout the event, we encourage you to engage with each other, ask questions, and share your own insights and experiences in the chat. We have a planisphere to give away tonight to a question that we feel is the best question of the night. So whether you're here to learn, to connect with others, or simply to enjoy some thought-provoking content, We are thrilled to have you here. My name is Petra, and I'm delighted to be here tonight to kick off what promises to be an exciting and informative event. So sit back, relax, and get ready for an unforgettable journey through the cosmos. Let's get started. First up for tonight's show is Jackie, and she will be explaining Lagrange points.
Where is the James Webb Space Telescope? The Webb Space Telescope is located at the Earth's L2 point. That's a Lagrange point, an area where the gravitational pull of two bodies is evened out and only a few corrections are needed to keep the smaller object in the same place. These were discovered mathematically by the mathematician Leonard Euler way back in 1750. He came up with the first three, and then the Italian mathematician Lagrange came up with L4 and L5. So they're named after Joseph Louis Lagrange, but he was born Giuseppe Luigi Lagrange. He taught himself maths when he was 17. He lived in Berlin for about 20 years and he spent his final years in France, which is why we know him by his French name. So L1 and L2 are on either side of the Earth, one towards the Sun, one away from the Sun. L3 is on the far side of the Sun, and L4 and L5 are these elongated areas around about 60 degrees either side of the Earth. Now, the Webb Space Telescope orbits the L2 point, so it's on the far side of the Earth from the Sun. It needs to be a little bit cooler and away from the Sun. Around the L1 point, we have a famous spacecraft who does watch the Sun. This is SOHO. It's been there since 1996. And it's been watching the Sun for us all that time. It's also discovered around 4,000 comets as they come in and pass the Sun. We don't have any permanent spacecraft at L4 and L5. We do know of a couple of asteroids who are stuck there at the moment, and we don't know of anything at L3. We certainly don't have any spacecraft there at the moment. In comparison to the Hubble Space Telescope, that orbits around the Earth quite closely, about 600 kilometres up. That was designed for the Space Shuttle to be able to visit it and do maintenance. In comparison, the L2 point is 1.5 million kilometres away. So the Webb Space Telescope is not designed to be visited or maintained.
Viewers now understand a little bit more about Lagrange points. We now have Murph taking us through a history of space telescopes.
Welcome back, Cosmos fans. Before we get down to the nitty-gritty of the James Webb Telescope, I'd just like to give you a little background of what we have sent up in space, what is still in space, and what is planned for space. Hopefully over the next few minutes I can help you understand the who, what, where, when, how, and especially why we have telescopes in space, and how do we communicate and get that data back. So why do we have telescopes in space? Well, when you look at the electromagnetic spectrum, where we get all our data from, most of it from gamma ray through to radio is actually reflected by the Earth's atmosphere. What gets through is visible light and radio waves, and we have ground-based telescopes to pick up that data and give us some wonderful images. A Hess telescope also picks up some high-energy gamma ray. In space, though, you look at this image and you'll see that the spacecraft named here roughly represent their electromagnetic spectrum that they're sitting above. Some of these craft are named after famous astronomers or the like. Others are just given the name, an acronym of what they're actually working on. How many telescopes are in space, you might ask? Well, it started back in the 1960s with the space race between USSR and USA, and Russia were first in 1965 to get a cosmic ray and particle detector satellite into space. To date, we have launched 90 observatories into space. 65 of those have ceased operation. They've either in a decay orbit and crash into the atmosphere and burn up, or some of them are sent into left in a permanent orbit. Currently, we have 25 active telescopes in space. Some have dual purpose, and most of them are single purpose. Dual purpose are examples like SWIFT. It's doing gamma ray, X-ray, ultraviolet, and visible light. There are a few ground-based scopes, namely visual or radio, as we've mentioned before. Planning is underway for 15 more telescopes to be launched over the next few years. The laser interferometer space antenna is probably one special unit and is planned for 2037, and that will be detecting gravity waves. Of the 25 active telescopes that we have in space, 6 of them are working on gamma ray, 7 on pure X-ray, 4 on ultraviolet, 4 on visible light. We have things like SWIFT that is working across those 4 things. We have infrared and submillimeter 2 telescopes. That's the James Webb and WISE. Microwave, we have 1 observatory called Odin from Sweden. And particle detection, we've got 3 observatories, including the IBEX, the Dark Matter Particle Explorer, DAMP, from CAS. Once we've launched our telescope in space, where are we likely to find them? Most of our telescopes are under 2,000 kilometers in low Earth orbit. A few more are at medium Earth orbit between 2,000 and 35,000 kilometers, and less so in the high Earth orbit of 35,000 kilometers or more. The Lagrange points have, well, at L1 we have the SOHO, which is observing the Sun. Gaia, Spectra, and JW are out at L2. L4 and 5 were host to the Solar Terrestrial Relations Observatory, but we lost contact with that back in 2016. And how do we operate a space telescope? Certainly not by magic. Basically, we can work out what we want to do with the telescope days, weeks, or months in advance, and when it's ready, we'll send the information to the telescope where to point. The telescope can use sensors and gyroscopes for repositioning and holding on a target direction. Detection and collection of electromagnetic radiation at various specific frequencies is the main aim of any one of our telescopes. Hubble's NICMUS, for example, senses infrared heat from objects in space. We'll process and convert the collected data into packets of radio signals and transmit that on a carrier wave to Earth receivers. We'll see more of that in the next image. Scientists and astronomers, etc., will decipher the received data, convert it to an image that we can understand. In general, communications are over what we call the deep space network. Using Hubble as the example, we can see that Hubble can be pointed to collect light from a distant object or area of space. It converts the data into a radio signal, sends the data to a relay satellite that is bounced to the ground receivers. Data is relayed to Goodard, and data is then converted to an image for distribution so that we can appreciate it. Yay! And who is the host with the most telescopes in space? Well, NASA win hands down. They've got 12 units up there, plus a couple more to share with ESA and or CSA. ESA have 4 units of their own, and another one that's shared with the DRDC. China has 3 units. India has 3 units. Italy, a couple. Japan, a couple more. Russia has 1, surprisingly, and it's shared with Germany. Austria, Canada, and Poland share 1 unit, and Sweden has 1 unit. Now let's have a look at some of the more famous telescopes that we've launched into space. Spitzer is an infrared telescope and a forerunner for the James Webb. It was launched 2003 after a lot of trials and tribulations. It was planned for 2.5 to 5 years, but lasted over 16 years. It ran out of helium in the end, which is keeping the system cool. It had an 85 centimeter Ritchie Crichton primary mirror, and its infrared cameras, etc. So we have one nice view there of the Crab Nebula. The multi-wavelength Swift telescope was designed to observe gamma ray bursts across the universe. It was planned for a 2-year mission, lasted 18 years, and in that time, well, after 12 years, it had recorded 1,000 GRBs, the most distant one being 13 billion light years away. From the several X-ray telescopes we have in space, Chandra is probably the most famous. Launched in 1999, planned for 5 years, and still going. It's got a 1.2 Walter type X-ray telescope, and the picture here is an image of an X-ray flare from Sagittarius A star. The IRIS, or Interface Region Imaging Spectrograph Observatory, was launched in 2013 into a sun-synchronous orbit. It's got an ultraviolet imaging spectrometer, and the image there is showing just one of the solar prominences. The Wilkinson Microwave Anisotropy Probe, launched in 2001, gave us one of our most famous photographs, an image of the background of the cosmic radiation. It had 2 Gregorian mirrors, oval shape, 1.4 by 1.6 meters, that were back to back, and measuring temperatures across the cosmic microwave background. And while we're all enjoying the fabulous images coming in from the James Webb Telescope, just have a thought about the scientists, astrophysicists, etc. who are planning for the future. NASA's gravitational wave detector, planned to go up in 2037, is probably a very ambitious project. ESA's planetary transits, oscillation of stars, it's an array of 26 refractors, each 120 millimeters diameter, and that'll be plotting the transit of planets across other stars. ESA are also sending up Euclid, which is a visible to near infrared with a 1.2 mirror, and to observe the extragalactic sky. And ISRO's X-ray palameter satellite is being sent up to observe pulsars, black holes, X-ray binaries, galactic nuclei, and a few other things. Finally, my thanks for listening and watching, and if anyone's interested in making a paper model, by all means search the web for Space Telescope paper models, or have a check out the link below from NASA. And it's back to Petra. Thank you.
Who would have known there were so many telescopes that have gone out to space? I can see questions already filling our chat. Please keep them coming as we have a planisphere to give away tonight to the best question. Neil is up next, explaining the engineering of the JWST.
The James Webb Space Telescope is a unique and advanced telescope that is set to revolutionize our understanding of the universe. However, to make it happen, there were many engineering challenges that had to be overcome. In this video, we will explore some of the key challenges that engineers had to tackle to make the James Webb Space Telescope successful. One of the most significant challenges was shooting in the infrared. Seeing the universe in infrared light will reveal many important details about some of the universe's greatest mysteries. However, infrared light is heat. Any excess heat in the telescope would completely overwhelm the faint objects it is trying to observe. To achieve this, the instruments have to be kept very cold. The solution was to make the telescope in two halves, with the sunshade keeping one side cool and the other facing the sun with the less temperature-sensitive equipment. Additionally, a cryocooler is used to chill the instruments down to their operating temperature. This is essentially a superpowered refrigerator, which brings the temperature down to 7 degrees Kelvin, which is about minus 266 degrees Celsius. Another major challenge was the mirror. It is huge and incredibly accurate. Multiple smaller segments make up the full size, so that the telescope could be folded to fit in the rocket. Using a segmented mirror also means that each segment can be precisely aligned together. They can withstand potential damage from space debris and still function as a whole. And it allows for more precise control over the temperature of the whole mirror, which is easier with smaller mirrors than one large mirror. Making the mirrors required them to have an extremely accurate shape and to be polished to be incredibly smooth. The telescope
Okay, everybody, just hopefully you can hear. We're having a little difficulty tonight. It seems like it's across all of us, so it must be an internet thing going on at the moment that we're all having problems. We are going to show you Neil's video again, as it seems like it didn't seem to play. So just hang in there and we will play that shortly for you.
The James Webb Space Telescope is a unique and advanced telescope that is set to revolutionize our understanding of the universe. However, to make it happen, there were many engineering challenges that had to be overcome. In this video, we will explore some of the key challenges that engineers had to tackle to make the James Webb Space Telescope successful. One of the most significant challenges was shooting in the infrared. Seeing the universe in infrared light will reveal many important details about some of the universe's greatest mysteries. However, infrared light is heat. Any excess heat in the telescope would completely overwhelm the faint objects it is trying to observe. To achieve this, the instruments have to be kept very cold. The solution was to make the telescope in two halves, with the sunshade keeping one side cool and the other facing the sun with the less temperature-sensitive equipment. Additionally, a cryocooler is used to chill the instruments down to their operating temperature. This is essentially a superpowered refrigerator, which brings the temperature down to 7 degrees Kelvin, which is about minus 266 degrees Celsius. Another major challenge was the mirror. It is huge and incredibly accurate. Multiple smaller segments make up the full size, so that the telescope could be folded to fit in the rocket. Using a segmented mirror also means that each segment can be precisely aligned together. They can withstand potential damage from space debris and still function as a whole. And it allows for more precise control over the temperature of the whole mirror, which is easier with smaller mirrors than one large mirror. Making the mirrors required them to have an extremely accurate shape and to be polished to be incredibly smooth. The telescope needs to take long exposures of very faint objects and keep still for hours at a time. However, the telescope is floating in space and not anchored to anything solid. To keep it still, it uses a two-part solution. Cameras to know exactly where it's pointing, and gyroscopes to turn and stabilize it. The cameras track guide stars to determine the position and orientation of the telescope, while the gyroscopes help maintain stability and point it precisely at its target. The JWST's Integrated Science Instrument Module is another crucial component that houses the telescope's 4 scientific instruments. These instruments are capable of detecting and measuring different wavelengths of infrared light, and are designed to work together and share data, enhancing the telescope's scientific capabilities. These are the heart of the telescope, and capture the beautiful images we see, and examine the light of the universe in incredible detail to reveal its secrets. To fit in the rocket, the telescope had to be designed to fold up, and after it was launched, deploy into a much larger instrument like a transformer. The mirror unfolds, the secondary mirror flips over the top, and the sunshade unfurls like a giant picnic blanket to cover the area of a tennis court. This all had to survive the violent shaking of a rocket launch, and then completely and perfectly unfold once it was in space. If even one step failed out of the 178 steps needed, then it could not have worked as well as planned, or it might have failed completely. Fortunately, everything went even better than expected, and as such, the expected mission duration may be able to be as much as twice as long as originally planned. The James Webb Space Telescope is an engineering marvel that required the collaboration of experts across a range of fields to make it a reality. From shooting in the infrared to designing a giant transformer-like instrument that could survive a rocket launch, engineers had to overcome numerous challenges to make the JWST a success. It is a testament to human ingenuity and our determination to unlock the mysteries of the universe.
Wow. Thank you, Neil. What a great success story. And now for a short news break.
On April 20, there will be a total solar eclipse visible from the northwest coast of Western Australia, referred to as the Ningaloo eclipse, as it will be visible from the Ningaloo Reef in Exmouth. This is the only land location in Australia.
Okay, I hope you're enjoying our show. Don't forget to hit that like or subscribe button. Okay, we will now have Steve be showing you some images from the JWST.
Thanks, Petra, and hi, everyone. My name is Steve, and I'm going to show you some of the wonders that the Webb telescope has discovered so far. It's only been 8 months, believe it or not, since the astronomical community was wowed by the release of the first science images taken by the JWST, but it's already revealed discoveries we couldn't have dreamed of beforehand. So what was the excitement all about? Let's have a look. The first thing to remember is that the JWST is all about shedding light on the origins of the universe. It will observe the universe's first galaxies, reveal the birth of stars and planets, and look for exoplanets that may hold the potential for life. No one has been able to do this until now, but already the JWST has achieved all of these science goals. To accomplish this, the JWST is bristling with cameras and spectroscopes and other instruments capable of resolving objects that are 9 times fainter than what the Hubble Space Telescope can. So what have these instruments revealed so far? For starters, Webb's infrared vision has helped us view for the first time the birth of stars and even planets, because infrared light does not get blocked by gas and dust. And this allows us to see objects that we simply can't see in the visible spectrum. Now here is a video which contrasts an image of NGC 3324 in the Carina Nebula taken by the Hubble Space Telescope with an image taken by Webb's near-infrared camera. So the first image is the Hubble, and as we sort of slide through, we can have a look at the image taken by the Webb Space Telescope. And as you can see, all of that gas and dust disappears. And for the first time, we can actually show the birth of new stars that are emerging out of the nebula. We've never been able to see this before. It's brand new science to us. So Webb's infrared vision has also allowed us to see objects that are incredibly distant and invisible to us, objects we've never seen before. This is because as the universe expands, objects a galaxy, well, as the universe expands, galaxies and other distant celestial objects are speeding away from us so fast that their light has become stretched and shifted to invisible infrared wavelengths. And beyond a certain point, the most distant galaxies are receding so quickly and their light has become so stretched in wavelength that they are invisible, even to the Hubble Space Telescope. It was not until the release of the JWST's first images that we got our first glimpses of what the universe looked like just after it began, some 13.7 billion years ago. Now, the image that you can see on your screen was captured by Webb's near-infrared camera and shows the galaxy group SM-ACS 0723, which is in the southern constellation of Valance. This galaxy group is shown as it would have appeared 4.6 million years ago. And the galaxy group are these little white blobs that you can see. They're a long, long way away, but the orange and more distorted galaxies that you can see have been gravitationally lensed by this galaxy cluster, and they're much, much further away. And we know this by measuring how much of the light coming from these galaxies has been stretched into the infrared part of the spectrum through a parameter called redshift. Now, just a few months ago, a redshift of 8, which corresponds to a time when the universe was about 646 million years of age, was considered a high redshift. With JWST, the record redshift is now 13.2, which corresponds to a time when the universe was only 325 million years of age. One of the galaxies in this image has a redshift of 13.1, meaning that it existed just 330 million years after the Big Bang. The JWST has also captured infrared light that has passed through the atmosphere of an exoplanet as it transited its host star. Now, this graph shows the amount of infrared light that has passed through the atmosphere of an exoplanet called WASP 96b. It shows what element blocked the infrared light at that wavelength. So we know that this planet has water vapor in its atmosphere. The graph also shows the temperature of the atmosphere and even that it has clouds, details that come from all of the peaks and troughs in the graph. While it has water in its atmosphere, it's far too hot to have life. However, the JWST is also looking at the atmosphere of many other exoplanets, such as those orbiting the TRAPPIST-1 system, which is a red dwarf star which is known to have 7 rocky planets in its habitable zone. And stay tuned for some exciting news about the atmospheric contents of these rocky planets in the next few months. But apart from the JWST science goals, let's just check out some of the first exquisite images revealed by the JWST. Now, this is an infrared view of Stephan's Quintet. This is a galaxy cluster located in the constellation of Pegasus, about 290 million light years away. It comprises 4 galaxies, which are gravitationally locked together. The 5th galaxy on the left, which is that one just there, is actually much closer at only 40 million light years. It just happens to be in our line of sight. Now, this is the Southern Ring Nebula. It's about 2,000 light years away in the constellation of Vela. The image on the left was taken in the near infrared, and the image on the right was taken in the mid-infrared. But the interesting thing to note is that the star responsible for the nebula is not the bright star that you can see in the center of this left image, this one here. It's actually the dimmer of the 2 stars in the center of the right image, this one just here. Now, this is the first time that this star has ever been seen, and that's the star from which the nebula has originated. Now, this has just been a brief outline of what the JWST has been able to discover over the last few months. Indeed, just the other day, the JWST revealed a previously unexpected benefit, the discovery of asteroids that could pose a threat to the Earth. But aside from its amazing discoveries, the dazzling beauty of the images is simply breathtaking. And all the data is readily available to access and even process yourself by going to the website you can see on the screen. So I want to encourage you to take a note of that website, have a go, download some images and be prepared to be amazed. Thank you, and back to Petra.
Thank you, Steve, for that interesting information, and I'm sure people are sure to go to that website. Okay, I've seen so many really good questions popping up in the chat. Keep them coming, as we will be giving away Planisphere tonight, the best question. All right, how images are built up from the collected data will be brought to you by Andrew.
Hello again, everyone. I'll be attempting to explain to you how something infrared can be turned into something we can see and appreciate. The James Webb Space Telescope photographs, how do they do that? These 2 images show clearly the difference between a Hubble and a JWST image. The Hubble telescope captures visible light, much the same way as a normal camera, collecting the light to build up the image, eliminating distortions and noise as the image becomes clearer and sharper. There is some enhancement of color and contrast, just as you can do editing an image on your computer or your phone. But the image is pretty much what you would see if you were in space looking through an actual telescope. Consequently, dust and gas clouds, as Steve was pointing out, either dark or glowing or reflecting the light of nearby stars, will obscure anything beyond what you are observing. The James Webb Space Telescope collects infrared light, light that our eyes cannot see. The advantage of this is that light at those wavelengths penetrates gas and dust clouds, allowing us to see further into the universe. The disadvantage is that if we made a photograph the same way as we do with the Hubble, we couldn't see it because we can't see infrared light. So how do they make the data from JWST into something we can see? Here behind the JWST mirrors, back here, there are 6 data collection components. Aperture masking allows for better resolution. A micro shutter array consists of 248,000 small doors that can open or close to assist in collection of spectra. It's remarkable engineering. Spectrographs separate infrared light into different wavelengths. 3 cameras sensitive to infrared light are collecting image. A combined camera and spectrograph captures an image along with spectra for each pixel, revealing how the light varies across the field of view. And finally, coronagraphs block the light from brighter objects, which would normally blot out dimmer objects. The data is distributed to 4 instruments. The fine guidance sensor is a guide camera that helps to point the telescope in the right direction. It's packaged together with the NIRISS, which has a camera and a spectrograph to take images and spectra in the near infrared range. The near infrared spectrograph, or near spec, has a dedicated spectrograph that can capture 100 spectra simultaneously with its micro shutter array. It's the first space instrument capable of taking spectroscopy for so many objects at once. The near infrared camera, it's the only near infrared instrument with a coronagraph. NearCam will be a key instrument for studying exoplanets whose light would otherwise be drowned out by their nearby stars' glare. It will capture high resolution images and spectra in the near infrared. Mid-infrared instrument, or MIRI. This combination camera and spectrograph is JWST's only instrument capable of seeing in the mid-infrared, where cooler objects such as debris disks around stars and extremely distant galaxies emit their light. Now, JWST has 27 filters that select a particular range of infrared wavelengths. In these images of the Tarantula Nebula, the image on the left was formed from data collected on a single wavelength, while the one on the right sampled over a wider range of wavelengths. The hottest stars are blue, so blue is assigned as the colour for shorter, high energy wavelengths, and you can see it's at 0.9 microns. Although we rarely see green stars, green is assigned for the image formed by a wavelength of 2.00 microns. Orange is assigned to wavelength 3.35 microns. And finally, red is used for a wavelength of 4.44 microns. So what happens when we combine these images? Well, when all the monochromatic images are combined, we get an excellent representation of the Tarantula Nebula. But when colour is added, the result is much more spectacular. So now you know how it's done. Back to you, Petra.
Thank you, Andrew. That was really interesting. It's amazing how to see those pictures come together. Okay, I would like you all now to stay tuned for our final news break.
After a year delay, NASA will launch the Psyche Discovery mission in October this year. Psyche, discovered in 1852, orbits the Sun between Mars and Jupiter. Psyche is an unusual metal asteroid, 95% iron and nickel. Scientists hypothesize that Psyche was a protoplanet forming during the early stages of the creation of our solar system. They believe Psyche was hit by other protoplanets or planetesimals, losing everything but its rocky core. The Psyche Orbiter spacecraft will orbit Psyche for around 21 months. The spacecraft is about the size of a small car and powered by solar panels. The Psyche Orbiter mission aims to map the asteroid and study its properties to find out whether Psyche was formed under conditions similar to the Earth's core, whether Psyche is a protoplanet core, and the age of different areas of Psyche's surface.
Okay, we all hope tonight that you've enjoyed our program so far. And if you have, please join us again for future shows every quarter, or you can rewatch any of our past segments on Facebook and YouTube. Finally, tonight we have Stu telling you about some discoveries made by the JWST.
Hello, everyone. So yes, I'll be talking about some discoveries from the James Webb. I can't hope to cover all of them, and even these discoveries I don't have time to really go into. So without further ado, here are some discoveries from the James Webb. Starting on the small scale within the solar system, one of the first things that the James Webb discovered was a micrometeorite, and it didn't use any of its very fancy equipment that Andrew went over and other such things. It did so through a permanent dent found on its primary mirror. Now, don't be worried. It's still, even with this dent, it's still working at above expected efficiencies and things, because they made it with such precision that that they expected things to happen like this, but and it will degrade over time, but it's still going strong for now. This image was actually a test image for tracking asteroids. It was aiming for the one down the bottom, but after this image was made public, a group of scientists found a smaller asteroid in the background, and they believe this asteroid is only a few hundred meters across, which might be big for everyday things, but for space it's very, very small. And this asteroid was also, I believe, a few 100 million kilometers away, so that gives you an idea of how good the James Webb is at looking at things. Here's a asteroid which is actually large enough to have rings. And we knew it did have rings before, but the James Webb was able to see the occultation of a star traveling behind the rings. The image here is just a visualization. The Webb didn't actually see that, but it did see the light from the star that it traveled in front of dim at these two specific points in its path. And from that, we were able to get more details about the size of the rings and what they are made out of. Still on asteroids, we had a recent DART mission which crashed a satellite at great speed into an asteroid and to see how much we could affect its orbit. And here's the James Webb videoing the crash in real time, and it sprayed out all of these dirt and dust globules and clusters. And yeah, sorry, this isn't in real time. This is sped up because space is big. But yeah, we can see that there's actually some structure to how it spread out. And all of this can tell you us a bit about the structure of asteroids. So we're learning lots. Up from asteroids, here's a picture it took of Jupiter. We can see all of its beautiful clouds, and we can even see at the north and south poles a beautiful aurora. While on Earth, it's a rather fleeting event, on Jupiter, these northern southern lights are actually permanent effects on the planet. We also see some of Jupiter's closer, smaller moons that you would have a lot of difficulty seeing, and even the rings of Jupiter. Yes, Jupiter has rings. They're just a lot dimmer and smaller than the other gas giants. And even in this image down in the bottom left, there's a small smudge. This is actually a galaxy. Galaxies are very faint, but they are everywhere. And it's very common for, if you look at nearly any image from the James Webb, to find a small galaxy in the background somewhere. And it's very likely we've never seen this galaxy before, brand new, and it's just there in the background, photo bombing the image. Here's the next gas giant out is Saturn, and here is its largest moon, Titan. The Titan has a very thick and interesting atmosphere, and they were actually able to even capture clouds traveling across it. So we can now get weather news from other worlds with the James Webb. And of course, here is Neptune, a very distant world. And we've never had an image of this high definition since a few decades ago when Voyager traveled past it. So we can now revisit the planet in some respects anyway. To the larger scale, we have interstellar epochs such as the Orion Nebula seen here. As mentioned before, we can now peer into the densely packed dust globules in which these stars form. And if you see it in the top right, we can now see the finer details of how the dust clumps together to form these stars in this stellar nursery. Here is a protostar up and personal. In the act of forming, all the dust is clumping down into a big stellar ring that will spiral down into the star. And this ring is a lot more dense and doesn't let light through. So all the light that we see is escaping up the top and the bottom of the disk in these beautiful arrays. Here's the good old Tarantula Nebula in all its glory, the largest star-forming region in the nearest 100,000 parsecs. Of the top 20 largest stars we've found, I think 14 of them are in this cluster. So it has a very impressive clump of stars here, and also very impressive dust clouds, which are being blown away by the interstellar winds. So there's a lot here to discover. Here's an interesting object, a Wolf Rayet star, which is a star which is especially good at throwing out interstellar winds and materials. And we believe this star is a binary star system with another star traveling around and every so often close by the Wolf Rayet star. And when they're very close together, their stellar winds interact and throw off even more material, creating these concentric shells of gas, which go off like clockwork. Here's an image of the Southern Ring Nebula, which I think was in another presentation, but they've looked at it in even more detail. We can see the structures of the gas thrown off here, and apparently some scientists are smart enough to look at this, and they were able to reconstruct some of the history of the exploding star, and they believe there was a number of stars very close to the progenitor, which influenced and warped the dust as it got blown away. The James Webb was also tasked with looking into exoplanets. Here is a star that was one star that was seen very close up. And no, we have not discovered that if you zoom in enough, we find that stars have 5 points. That's just a symbol to show where the star is. The actual starlight has been blocked by a special filter so that we can see the relatively very dim disk of gas around these very young stars, and this disk will eventually form planets around these suns that we believe. Here's a graph of the starlight reaching us from a distant star, confirming one of the first exoplanets that the James Webb has found. with that dip as the planet traveled in front of the star. And we got this dip with such detail that we were able to determine a lot more other things about the planet, such as its orbit and, of course, the composition of its atmosphere. This is from another dwarf exoplanet, but it's a similar thing. From the spectra of light from the sun, we can see how that changes when the planet goes in front of it. And this is the spectra of molecules that we can find in the atmosphere of the exoplanet. So this will be very interesting to look into what molecules are actually in the atmosphere of other planets. And that will be a definite indicator to whether there's even life on that planet, if you see lots of oxygen, for example. But yeah, that'll be very interesting for general dynamics of exoplanets. And here is a very special image of an actual exoplanet itself. Usually they're very close to the sun. The only things we see from them is when they travel in front of the sun and dim its light. But here is the light from an actual exoplanet. So if you see any images in the media when they announce we found another exoplanet, or this one's interesting, and it's more detailed than this image, then it's just an artist's impression, because this is one of the most detailed images of a distant exoplanet that we have. Of course, the James Webb can also see galaxies. Now, you've been shown before that the James Webb can specifically look in wavelengths that see through dust, but it can also see in another bunch of wavelengths that are especially good at being blocked by dust. And there are some scientists that are very interested in this because we can see the dynamics of dust themselves. These giant clouds, as they're blown away by stars and how they warp and clump together to form stars. It's all about the structure of galaxies. And to that fact, we can see distant galaxies with this frame of reference and see the actual structure that the dust forms. We believe that these kind of bubbles in the dust that you see here, all these holes, are formed by supernovae as they blow the dust out, or giant star clusters which have new bright stars that all throw the dust away from themselves. So this is the actual structure that we see in galaxies. And of course, the James Webb does see a lot of galaxies. Here we have a star cluster known as, I think it's the Pandora cluster, a giant group of galaxies, but most of the galaxies in this image are even further away than the cluster. It's just in the foreground. And one group of scientists tried to categorize all of these galaxies, and they counted 50,000 galaxies in this one image, or, well, number of images here. But yes, that's just... That's so many galaxies that the James Webb can see and has allowed the scientists to study. Of course, you might have seen in some images, this curving of the galaxies. This is due not to camera lensing effects, but to gravitational effects by large masses. So by looking at these distorted galaxies, we're able to determine the distribution of mass in these galaxy clusters in the foreground, which is all very interesting. Here's a group of ultra diffuse galaxies, which is a relatively recent category of galaxies that's been discovered. And now that the James Webb is up, it's having its go at looking at a few of these. They're relatively close, but very dim, but very interesting for the history of galaxy formation and such things. And although those were nearby, these galaxies are very far away. But they have been found to be extremely huge. So the James Webb is finding a lot of different, even new type categories of galaxy. Galaxies this large might even get in the way of some of our models about how quickly they can form in the universe. So yeah, we'll have to keep an eye on them and other galaxies that the James Webb finds. So of course, I've already gotten into it, but the James Webb can see very far into the past. So here is the earliest spiral galaxy ever seen, where we can even distinguish the spiral arms in this one. And we believe that this is forming around the time that we believe the first spiral arms were forming. So it's a good confirmation of work 11 billion years ago. Here's the furthest found star clusters by the James Webb. And in this image, we also have the furthest star ever seen, called Earendel from Lord of the Rings. Though technically James Webb wasn't the first telescope to actually see this star. This was known beforehand, but yes, still good to see it in more definition. Here is the furthest galaxy cluster ever found. And hopefully 13.1 billion years later today, these galaxies will probably still be chilling out together in the universe. Here we have an image of what we believe is the earliest found galaxy merger of two galaxies colliding, galaxy A and B up the top here, and this C is expected to collide later in their life. And of course, the furthest ever galaxy or object ever found in the universe. Well, technically, maybe not. There is one other contender that was discovered by a ground-based telescope that's around the same distance as the furthest one that the James Webb found. But it's still very, very impressive that the James Webb was able to see something that's 13.5 billion years in the past, or 13.5 billion light years away from us, near the start of the universe. We only expect the universe to have started 13.7 billion years ago. So this is in the first 100 to 200 million years, which is very early for galaxy formation. So yes, I've only touched on these topics just briefly, and the topics I've touched on are only a small touch on the research that James Webb has offered. In only its first year of observations, the data that it has produced has contributed to hundreds of scientific papers and has been referenced in thousands of scientific papers. So even though these distances seem impressive, we know that it will find many, many more in the future in its hopefully long reign in the sky, and find many interesting objects of note. So thank you for listening.
Thank you, Stu. Just mind-blowing discoveries and data already. That's just incredible in its first year. Okay, that was the last of our speakers for this evening, but stick around to learn more about who we are and what MBO is about before we head into questions and answers.
Mount Burnett Observatory is a community-run astronomical society in the Dandenong Ranges. We are completely volunteer-run and have over 500 members. We focus on community engagement, outreach, diversity, and helping our members to get the most out of their love of space and astronomy. The observatory was originally built by Monash University for students to do astronomical research, especially on variable stars whose brightness changes over time. Over the next 2 decades, the site was expanded and upgraded, but eventually took a back seat to modern giant internet-connected observatories around the world. In 2011, our 5 founding members reached an agreement with the landowners and took over the lease and established a society. Now, we run over 80 events each year, including members' nights, public viewings, and special events. We have several special interest groups, including deep sky observing, radio astronomy, astrophotography, astro arts, and young observers. In 2020, we expanded our online presence and now host regular live streaming events. We welcome all new members and love making new friends with other astronomy lovers. You will be joining a friendly community of passionate, hard-working amateurs who have a grand vision for the future of the observatory. We hope to see you up at MBO soon.
Hello everyone, we hope you are enjoying the stream. Coming up next is the question and answer segment, but first, some important messages. MBO is a volunteer-run organisation. If you'd like to support us, consider becoming a member, buying some MBO merch, or making a donation. You can find us on social media at these addresses. The live streams are created by a talented and diverse team. You can read the names of those involved below. Now it's time for Q&A.
Okay, so tonight we were going to have our young Ella show a presentation, but due to technical difficulties, unfortunately, she won't be able to join us. So I now invite all the panelists to join me for Q&A, and I'm going to go and have a look at some of the questions that you've been putting up. They're quite interesting. All right, we're all coming in. Okay, I'm going to have, so well, Stuart, seeing you were the last, let's start with you. Mark from Facebook is asking, is the universe expanding at a constant or increasing rate? And how do we measure this?
Yeah, this is basically the big question in cosmology at the moment. We believe the current model that we have of the universe is that the universe is accelerating in its expansion. So it's traveling. The galaxies are all traveling away from each other, and in the future they'll be traveling even faster away from each other. And it's a big question about why that's occurring, because we would first think that gravity would help try and pull the galaxies back together and slow the expansion. But the observations that we use to try and confirm this is just looking at very distant galaxies and comparing their distance away from us with their speed away from us. And generally, the further you get away from us, the faster it is the galaxy is traveling away from us. And if we plot all of those out, we can kind of see a history of how quickly things are moving away from each other in the universe. And actually, one of the many things that I wasn't able to touch on is that the James Webb is being used to double check a lot of those distance measurements. Because where there's actually a few things that we needed to, in cosmology, that we need to check and make sure they're super accurate, because they don't seem to be lining up in the very extreme cases. So the James Webb is looking at stars and measuring how far away from they are from us at new unprecedented levels to make sure that we've got all those distances correct.
All right, thank you, Stu. All right, I'm going to look at some questions, and I'm going to, Jackie, this question is for you. It's from Lockie. He's 12, and it's from Facebook, and he's asked, how do they know which star is the source of a nebula?
Yeah, this is a really good question, because often when you look at all those wonderful pictures, they all look flat and it looks like everything's at the same distance. So it can be a bit hard to tell what's actually going on in the picture. So we need to train our minds to see things a little bit in 3D, but we also need to understand what type of object we're looking at. So in Steve's talk, when he talked about there was a star in the middle of the nebula that was powering it up, we know these types of nebulas, they're called planetary nebulas. And it's a bit of a funny name, but the famous astronomer William Herschel gave it those types of nebulas their name because they like the planet Uranus, which he had found. When we look at them in our telescopes at the observatory, these nebulas look roundish and sort of an aqua Uranus looks like as well. But they're actually stars that are dying as it's shrunken, it's private light and the gas blown off greatly. And this phase only lasts 10,000 years, which is a blink of the eye in we know that's there, so we know that they're right in the middle of the bright ring that's showing in those pictures. So that's why we know that there's a other nebulas, there's different things going on. We know roughly where to look, and sometimes you which because we've got now 140 years of photographic evidence, so we can actually measure the direction stars are traveling. So if they're actually passing bits of dust, Neil, I think he's got that with a typical blue glow, and that's light reflecting off dust. So one, we sort of need to know a little bit about the story of the nebula, and here it is.
Thank you, Jackie. Okay, so we are now. I'm now going to ask you, Merv. Catherine from Facebook has asked, does Australia have any plans to send up its own telescope? You'll have to unmute yourself, Merv, so we can hear you, buddy.
Okay, sorry about that. Yeah, Australia does have one tiny little telescope in space at the minute. It's called Spirit, and it's a joint thing with the Italian Space Agency. It's the forerunner to a unit called Skyhopper, which will be a infrared, near-infrared telescope, and it is planned to look for, let me see now, gamma ray bursts, looking for extrasolar planets in around coldest stars in the neighborhood, and also having a look at the cosmic infrared background. So a little bit of excitement for us. That's going to be launched hopefully next year.
Great, thank you, Merv. Okay, so we are going to have our final question, and this is for you, Neil. And this question is the winning question for tonight. So the question is from Dot of Facebook. What is the most enlightening and unusual data that a telescope has picked up?
Well, I think this is a little bit of a hard question to answer because there's so many different things that could be. Space telescopes have provided us with such an incredible variety of astonishing discoveries. And I'm sure each of the people on the panel here would have their own favorite. And hopefully we can hear from them about that. But I'm just loading up an image to show you my favorite. I think is probably the most significant discovery by a space telescope. Oh, thank you, Aki, for moving my microphone out of the way again. So you might have heard of something called the cosmic microwave background. Let me just share my screen. Where are we? Here we go. This will do. And we can put that up. There we go. So this is an image taken by the Cosmic Microwave Background Explorer, which is a space telescope that observed in the microwave frequencies of electromagnetic radiation. And the single goal of this telescope was to map the entire sky at a particular frequency of light that is actually the echo of the Big Bang. So when the universe was formed in the Big Bang, it was initially dark because it was so dense, photons couldn't escape, they couldn't bounce around. But as soon as it spread out enough and cooled down enough that photons could be created, the entire universe was glowing. Everything in the universe was glowing. As then the universe continued to expand and expand at a tremendous rate. And as it did so, the slight variations in that density of the energies that were being given out by the light from that early part of the universe, those variations expanded. And we can see them here in this photo. So this is a compilation of images that taken up of the entire night sky, showing the different intensities of the microwave radiation, which is the afterglow of the Big Bang. And you can see it's not smooth, it's not continuous. And that one discovery even though we don't know how or why the universe isn't smooth, but the one discovery shows that this is where the structure in the universe came from. This is why we have galaxies. This is why we have galaxy clusters. If the universe was completely smooth, 100% homogeneous throughout, then every particle would have been equally attracted to every other particle. And therefore, it would have stayed in some sort of limbo, in stasis, and nothing would have changed. It just would have gotten colder and colder and darker as it expanded. But because we have this variation, everything we know, every part of the universe, every star exists. And we don't know why yet that random variation was there. There are a few interesting theories, but this photo is the first evidence, first proof that the variation existed right back at the beginning of the universe. And just a little bit of trivia to go along with this. The microwave radiation that you can see here, it was incredibly faint and the variation was incredibly small. So the difference between the red parts, which are sort of the more dense, and the blue parts, which are very faint, was so infinitesimally small, almost impossible to measure. But if you turn on an old analog TV or tune an analog radio, about 10% of the static that you will see and hear is actually the leftover, the echo of the Big Bang. It's this microwave radiation. So next time you get stuck looking at a TV that's all fuzzy with static, think that you're looking at the echo of the Big Bang. And it really helps bring it home how big that thing was. I'd love to hear if anyone else has a favorite discovery, a most surprising discovery that space telescopes have shown us.
Yeah, I might have a quick addition. If you wanted to share my screen, I've just put on one of the images from my presentation. I don't want to put this down as my definite best space picture or discovery because there's just too many to think about at the moment. But this image, when it was released or when I first discovered it relatively recently in the last month or so, I found a high definition image of it because you can really zoom into all the galaxies in the background there. And I spent literally about an hour just kind of scrolling through it, just looking at all the galaxies and amazing details that the James Webb was able to uncover here, because it really gets these high definition images that you can see. And also galaxy groups are just beautiful. They've got all these beautiful displays of light and shapes and interactions dotted around across the sky. So yeah, that's my beautiful image to add there.
Thank you, Neil and Stuart. Okay, Dot, don't forget that you need to provide us with your details by using the email prizes@mbo.org.au so that we can send your prize out to you as soon as we get a chance to. So, what an incredible journey and technical difficulties we've been on together tonight. We spent some time exploring the wonders of the JWST and its mission to unravel some of the deepest mysteries of the universe. Tonight, we've learned about the technology behind the JWST, from its giant primary mirror to its advanced sun shield that will protect it from the heat of the sun. We've also heard about the exciting discoveries that scientists hope to make with the telescope, from the formation of the first galaxies to the search for habitable exoplanets. We must remember that this is just the beginning. The discoveries that await us are boundless, and we have the potential to learn more about the universe than ever before. The JWST will serve as a window into the past, allowing us to see back in time to the earliest days of the universe. It will also help us understand our place in the cosmos and perhaps even find evidence of extraterrestrial life. So, as we bring this event to a close, I want to thank all of you for joining us on this incredible journey. I encourage you to stay informed about the JWST's mission and the groundbreaking discoveries that it will make. The future of space exploration is bright, and with the JWST leading the way, we are sure to uncover some of the universe's greatest secrets. Thank you and good night.